we get set up, we'll have Fabian Zaiser speaking about incremental density computation for efficient programmable inference.
Thanks. All right. So what I'm presenting today is joint work with Jack and Alex, who are here, and Vikash. And to start with, I want to show you a little illustrative example. So suppose you have some data points like these, and it looks like they come from two different clusters. And now suppose you want to infer the latent clusters from this observed data. So you want to get to this ground truth here. One way you could do this is to write a generative model in a probabilistic programming language. So this might look something like this, where you have some prior distribution, which I didn't specify, for the parameters for the clusters. And then you sample two parameters, one for each cluster from the prior. Then you sample cluster assignments for each data point from 1 to n from a Bernoulli distribution. And finally, you sample the actual data points from a normal distribution whose parameter depends on the cluster assignment. So if you run this program, it will generate data sets like the one I showed at the start. But what we want to do in practice is, of course, given a data set, find out what likely parameters led to this data set. So we want to do inference. We want to find execution traces that make the data likely. And what does likely mean? Well, it means we want to find traces that have a high density. And the density function is just basically multiplying together all the probability density functions of the distributions we sampled from. So how do we actually find good traces? One approach might be the following. So in Markov-Chain Monte Carlo, we start with a random initial trace, which does not explain the data very well. So you can see from the visualization it doesn't really fit. And also the log density is quite high, quite low, sorry. And then we try to improve it step by step. So if we want to draw L samples, we're going to have a loop here, and then make changes to the initial trace. So first of all, we might reassign the data points to different clusters. So we look at each data point and consider switching it to the other cluster. And we do that depending on the density of the changed assignment. So you could do like skip sampling here, or also an accept reject step. And after we've done all this, we also want to update the parameters based on the new assignment. And we keep going with this. So what you might have noticed here is that we have to evaluate the density function many, many times, and also typically on very similar traces. So doing this naively is kind of wasteful. So if you do this in a naive way, you get quadratic scaling here, which you can see here. But if we're smart about this and compute this incrementally, we get a much gentler slope like here in the data size. So for this simple example, it's kind of not a problem to do this by hand, but for more complex models, you wouldn't want to do this because it's very easy to make mistakes. So we want to automate this. And there's a couple of challenges with doing this that existing systems have encountered. So first thing is, how do we actually represent changes? So here we're in a setting where the user can write an inference program. So the user can basically decide what changes are proposed, and the system does not control this. Also, we want to support a broad range of possible trace updates. For example, splitting or merging clusters in more complex models, or in open universe models, we might want to add or delete objects or entities. We might want to modify subtrees of an AST, like in Maddie's talk on program synthesis. Or might want to do gradient-based parameter updates. And we want to represent all of these kinds of changes in a concise and efficient way. And just to give an example of what could go wrong in many systems, existing systems, if you delete an object in an open universe model, this leads to all kinds of indices being shifted around. And that kind of blows up the change representation. And we want to avoid that. So the second challenge is how to actually automate this in an efficient and correct way. So ideally, we want to achieve the same asymptotic scaling as a manual incrementalization. And for this, we're probably going to have to reuse intermediate results. How exactly are we going to use these? We might organize them in caches, but how do we thread all these caches around the program? And most importantly, how do we reason about the correctness of this whole mess? So our approach for dealing with this is the following. So one key realization regarding the change representation is that the kinds of changes we want to make really depend on what kind of data it is. And this is why we go for a type-driven approach. In particular, we use trace types, which have been mentioned in another talk before already, which have been used for other purposes in the past already. And we're going to combine that with another kind of types, which are change types. So these were introduced in the incremental lambda calculus. And yeah, these two kinds of types have been used before, but we combine them in our framework. So what are trace types? Well, trace types track what random choices a probabilistic program can possibly make during its execution and organizes that in a data structure. And the data structure also reflects the control flow of the program. So if we just have sequential samples in a program, that'll be recorded as a record. So we have this kind of record type with labeled fields. If we have a loop from 1 to n, then the trace type of this will be a list. And in our work, we actually also have a construct for exchangeable sequences. So we can also iterate about a set. And in that case, the trace will be an unordered collection, like a map. And when you actually write a model, you're going to annotate this with a type. So prob just says it's a probabilistic computation. And it has a result type, as usual, but it's also annotated with this trace type here. So this is the example from the start. And this trace type kind of fixes the type of the values that inference algorithms will make changes to. So this is the first ingredient. And the second ingredient is change types. So those describe the changes that values of a certain type can have. For example, for basic types, we might just have a replacement change. Just tells you whether it's the same as before and what the new value is. For record types, we'll just have subrecords, which include just the fields that changed and their changes. And for lists, we might just record removals, insertions, and modifications. And the inference programs that the user writes are actually going to generate such change descriptions, which are change types of trace types. As an example, if we have this kind of trace where we have a number of objects with certain positions, and we want to remove the first object, then the change will look something like this, where the number of objects is not the same as before and is now 2, and the first index of the positions list was removed. And this is kind of a smaller change than if all the indices shift around. OK, so how do we actually do correct and efficient automation? Well, doing this correctly is difficult because in a probabilistic program, you have random dependencies for variables, and even some variables might exist only in some branches stochastically. So we decompose this into 2 stages. The first one takes the probabilistic program with a generative model and turns it into a fully deterministic density function. And as a second step, this deterministic program is incrementalized to an incremental updater, which is then used by the inference program. So yeah, in the first step, we take this probabilistic model with a prop type, and turn it into a density function, which takes the trace as input, returns the result, and also the weight, or the density. So this kind of transformation is usually routine, but in our setting, it's a bit more subtle, because we have these exchangeable sequences and name generations, which makes this a bit more complicated. If you're curious, talk to us in the poster session. The second stage is the actual incrementalization. So this is inspired by the incremental lambda calculus. And The idea is that we have a deterministic program from inputs to outputs, and the incremental version, in addition, also produces an updater from input changes to output changes. So this updater is a co-inductive type, which looks something like this. So it's essentially a function from input changes to output changes plus a new updater for subsequent changes. And this kind of packages up and encapsulates the caches for intermediate results, which we need for faster incremental updates. How do we actually produce these updaters? Well, for primitives, they just have their own specific updater versions, and the translation rules for the transformation compose them together. We have correctness proofs for these transformations based on denotational semantics and logical relations. And we also have a prototype implementation where we compared this to a non-incremental version and to Gen's incrementalization on a couple of models that are kind of challenging. And we implemented a couple of MPMC kernels. And the takeaway is that our method in blue is the only one that achieves the desired asymptotic scaling in the data size for all models and kernels. Yeah. Thanks for listening, and look forward to questions.
Thank you. We have time for a question or two. And could the next speaker please come up? You can plug in.
Okay, thank you for the talk. I'm just interested in what is the expensive part of your original computation? Is it really a lot of the same computation happens, or you have to then you can just directly reuse the intermediate results, or you also have to perform different kind of computations in the incrementalization